Well, first of all, I want to apologize for speaking English. It's kind of disappointing because Ukrainian is the language of my friends, of people with whom I increasingly identify. I was too distracted by other things recently, but I will improve. So I will share the screen. Of course, in Kyiv, I should speak about growth. By the way, recently, until recently, I was an honorary professor of the Kyiv University, but now I moved to being a real one because I gave a course of linear algebra, which is something real. Okay. So I will talk about growth functions of algebras. Let F be a field, and let A be a finitely generated F algebra. I did not specify if A is associative or Lie or anything else. Suppose that the algebra A is finitely generated. So it is generated by a finite dimensional subspace V. Let Vn, well, in these round brackets, is a span of all products in generators from V of lengths up to n. With if A is not associative, then with all possible brackets. In any case, this is a finite dimensional space. And we have got an ascending chain of these finite dimensional spaces. The union of them is the whole algebra. Now, the dimension of Vn is called the growth function of this algebra A with respect to the generating subspace V. Unfortunately, it depends on the choice of the generating subspace. And therefore, we have to introduce a certain equivalence. Let n be the set of positive integers given two, say, increasing functions from n to positive real numbers. We say that f is asymptotically less or equal than g if there exists a constant c such that for all n's we have this inequality. If f is less or equal than g, and g is less or equal than f asymptotically, then we say that they are asymptotically equivalent. This is a very rough equivalence. For example, all polynomials of degree n, no matter what coefficients are asymptotically equivalent. And all exponentials e to the power alpha n are also asymptotically equivalent. Now, if V and W are two generating subspaces, then the growth functions with respect to these subspaces are asymptotically equivalent. So the growth of an algebra is a class of equivalence with respect to asymptotic equivalence. Recently, last year, we, in a joint paper with Jason Bell, we described the class of functions that, up to asymptotic equivalence, appear as growth functions of finitely generated associative algebras, and the same class appears as class of functions of finitely generated semigroups or even hereditary formal languages. And I talked about it at the end of 2020. But I will recall the theory. Let f of n, capital F, be an increasing function. Consider its discrete derivative. If this discrete derivative satisfies the following two properties, then the original function is asymptotically equivalent to a growth function of, say, a finitely generated associative algebra. And every growth function satisfies these properties. So this is a description. The interesting feature of this description is that before the question was if, say, submultiplicativity of the function is enough, for it to be a gross function, the answer is no. The conditions should be imposed on the derivative, which is stronger. Now, let us talk specifically about nil algebras. An associative algebra is called nil if an arbitrary element is nilpotent. So for an arbitrary element, there exists some positive integer such that we have this equality. But of course, this integer depends on the element. And for many years, it was an open problem if there exists a finitely generated associative nil algebra, which is infinite dimensional, which with polynomially bounded growth function. That would be a much stronger version of the solution of Courage problem, because in groups, there are no periodic finitely generated infinite groups with polynomially bounded growth functions. However, to the surprise of many, Tom Lenagan and Agatas Maktonovich constructed examples of such algebras over infinite fields, over countable fields. The question about the existence of such examples over uncountable fields is still not known. Jason Bell and Alex Young showed that over uncountable field, you can get a nil algebra sub-exponential growth. And actually for any super polynomial function, maybe sub-exponential function, you can construct an algebra with growth function less than it. It was essentially the first new example of a finitely generated infinite dimensional nil algebra after the celebrated examples of Golat. Now the question is, what are possible growth functions of nil algebras? My conjecture is that if we don't consider small cases, that is, if we only consider functions that are asymptotically greater than, say, n squared, or if you insist n cubed, then the class of growth functions is the same as the class of growth functions for all algebras. In a recent joint paper with Beery-Greenfield, we proved the following theorem. If the field F is countable and F is an increasing submultiplicative function, and delta is an arbitrarily slow growing function, non-decreasing, that nevertheless tends to infinity, then there exists a finitely generated nil algebra with growth function that lies in this, well, that satisfies these inequalities. So that is sufficiently, that is pretty close to F. Well, the construction uses Riesz product of matrix, Riesz product of algebras. Well, for an arbitrary field, not necessarily countable field, there is a somewhat weaker statement that for any non-decreasing function omega that is super polynomial, and for any non-decreasing function delta, there exists a finitely generated nil algebra that satisfies this inequality. So the philosophy is the same. It is close to the function f of n. Now, I want to talk about algebras with oscillating growth functions. Martin Kasabov and Igor Pak, when constructed a finitely generated group with oscillating growth function. So for infinitely many n's, it was less than one intermediate function, and for infinitely many n's, it is greater than, well, arbitrary sub-exponential function. That is, choose an arbitrary sub-exponential function which is bigger than this one. Then infinitely many times it is less than small function, and infinitely many times greater than the big function. So it oscillates. Then, and basically, Kasabov Park example was, well, from people who are sufficiently far from the subject. They are Grigorchuk type groups. Maybe people who work in the subject, they distinguish between subclasses. Then Viktor Petrogradsky last year, for an arbitrary prime number P, well, he constructed a class of, well, he and also Ivan Shostakov and myself, we constructed a class of Lie algebras that are very close to groups of Grigorchuk types, somewhat close. And he used these algebras to construct finitely generated Lie P algebras with oscillating growth. So, well, now another theorem joined with Beery-Greenfield is that for any field, even a field of zero characteristic, there exists a finitely generated nil algebra with oscillating growth function. Then if you want to get nil Lie P algebras, as in Petrogradsky's work, you just have to take A minus. Every associative algebra gives rise to a Lie algebra. Well, and there exist even domains with oscillating growth functions. Now, I want to mention some application of this oscillating growth functions to a question about Gelfand-Kirillov dimension. Now, given a finitely generated associative algebra, which has polynomially bounded growth, we look at all these powers that bound the growth function and choose the infimum of all these alphas. This is Gelfand-Kirillov dimension of a finitely generated associative algebra. Now, Gelfand and Kirillov in late 60s, they needed to introduce an invariant for infinite dimensional algebras to distinguish between them, to prove that some infinite dimensional algebras are not isomorphic. And so they introduced this invariant. It kind of measures the type of growth, but only for algebras with polynomially bounded growth function. If the growth function is not polynomially bounded, then we say that the Gelfand-Kirillov dimension is infinite. Now it is easy to show that if we have a tensor product of two algebras, then the Gelfand-Kirillov dimension of the tensor product is less or equal than the product of Gelfand-Kirillov dimensions. However, this inequality may be sharp. Bill Warfield constructed examples, and as a strong form of these examples, he proved the following thing. I cannot remove some part of my screen. Okay. He proved the following thing, that for any alpha and beta greater or equal than 0, because if the Gelfand-Kirillov dimension is less than 2, greater or equal than 2, if it is less than 2, these algebras are very small. They satisfy polynomial identities. They are kind of close to polynomials in one variable. And so he proved that for any such alpha and beta, and for any gamma that lies in this segment, there exist algebras A and B with Gelfand-Kirillov dimension alpha and beta, and Gelfand-Kirillov dimension of the tensor product is gamma, which could be essentially smaller than alpha plus beta. But his construction was more or less a play with radicals. And independently, Krause-Lenegan and Krempa-Akninsky formulated the question, what about we cannot play this game? What if the algebras A and B are semi-prime? Do we still have sharp? Can we still have sharp inequality? Now we used these algebras with oscillating functions to prove that yes, this conjecture, the same results, that we constructed algebra, even primitive monomial algebras, for which gamma can be attained. Well, I guess I was given half an hour, but I'm more or less finished, using essentially half of the time. Well, it's because I did not say much about proofs because they're technical.